All right, why don't we get going? So last time we started to learn a little bit about networks in this final little part of the course. We're going to make that a little bit more practical today by actually looking at code that you can use to access other machines and talk to other machines or build communication protocols or build a web server or build a distributed system. Really the heart of all systems today that you use on the internet, etc., comes down to these very simple things, like being able to communicate between two machines. And so we're going to learn about one particular interface that's so widespread these days. It's called the socket interface. It's basically a very standard way of communicating across many different platforms. It was invented, about 30 years ago, as all this stuff was starting to come into place, and then became basically a de facto standard interface to the protocols that we were talking about last time, like TCP/IP and UDP/IP, those generic internet protocols. I might close the door over here. So I think from last time, not many people had done any socket programming. Is that right? A little bit, maybe. So not too much. Okay, so hopefully we'll learn something about that today. And we'll just look at code and talk about the important pieces of code. In general, socket code, when you look at the code, and we'll look at very small code snippets today that demonstrate how you build a working communication stream between two processes on different machines or on the same machine, doesn't matter. But if you look at the code, if you mess any little tiny thing up when you're doing this type of code, which is true, of course, in a lot of things in C and Unix-based systems. But these little tiny things, if you get them wrong, things will fail in very strange and odd ways. So you really have to be very careful when you're just crafting the very basics of how to set up a communication channel and then use it. And once you get that stuff working, well, then it's usually not that hard to build on top of that and build the more interesting services and applications that you're trying to build. So pay attention to the details, and certainly where you can, use code that you know that works instead of just reinventing everything from scratch. Okay, so first thing we're going to talk about are how do we actually, yeah, that's a question. It is recording right now. Yeah, good question though. So now your attention level can sag somewhat. Yeah, his head immediately falls down, back to sleep. Yeah, it is being recorded. You never know though, like the recording might fail in some way. So it's a probabilistic thing. Most likely it'll make it, but who knows? Okay, so in any case, we start with, the first thing you have to start with in any communication system is an address. You need some way, or a name, really some way of referring to some other thing that you're talking to or want to talk to or communicate with. And in the internet, the global IP internet, or we'll just call it the internet, capital I internet for short, that's done via IP addresses and on top of that, host names. So an IP address is a pretty simple thing. You can find out what an IP address is for the machine you're running on. Here I'm running on this machine called Claudio, and I could run this program called hostname -I, and it'll give you this thing. You've probably seen a lot of things like this before when you're using the internet. That's an IP address. An IP address is actually a very simple thing. It's just a 32-bit entity, just a 32-bit number. But it's usually shown this way. It's what's called dotted decimal notation. So you take each byte and then say what that byte value is. So that means each of these values between the dots can be between 0 and 255. So it's not that exciting, but when you see this, all they're reporting to you when they report an IP address in this form is the 32 bits that make up the IPv4 version 4 address. Now you can imagine when they invented the internet, right, when these standards were being settled upon, that 32 bits, 4 billion hosts, seem like a big number, right? Hey, who would ever imagine? They were connecting hundreds, thousands of machines back then, so they figured 32 bits, really forward-looking. And of course, as you personally have more and more devices that access the internet, those 32 bits are problematic. And so we're slowly running out of space, and because of that, you may have heard of this thing called IPv6, which allows for larger addresses, right? More address bits. So as always, we always talk about this in systems in general. When you're picking some number of bits and you think you're forward-looking, you should probably double it or do something, a little bit more than you would think that you need, because when you run out of those bits, it's a huge pain. And it's taken for IPv6, the version has more bits than these 32 bits, has been around for years, but it takes forever to get something like that deployed and in wide use. And so people have all these clever workarounds for what do you do if you can't assign every device its own IP address, so you do it dynamically, do all this crazy stuff, and you may or may not know more about how that works. You can certainly go look it up. But it's a pain, and that pain derives from this decision made long ago, which is, hey, let's just have a 32-bit address. Okay, so does that make sense? We'll just view the world very simply, which is not quite accurate, but the simple way to view it is when you are on the internet and you want to communicate with someone, you have an IP address, and that's the 32-bit number that someone, to route a message to you, they need to be able to know that number, and then they submit it to the network, and the network needs to figure out how to go from wherever you are to wherever that thing is. Make sense? Kind of simple. All these ideas are simple, right? But that's true in computer systems in general. Now, of course, at some point somebody said, these IP addresses are great, but they look like things computers can deal with, but of course, it's not that great for humans. When you want to say, hey, can you connect to this web service, or you want to log into this machine, you probably don't have to say, okay, let's log into 128.105.166.120. It's not that amenable or friendly for humans. And so, of course, people came up with a very simple idea of let's have names that we can use that are more sensible. And so you can find out the host name of a machine that you're running on just by, remember we did hostname -I for finding out the actual 32-bit internet address. If you run the program hostname, you can find out what the name of the host is. In this case, it's claudio.cs.wisc.edu. And you can see a couple things about this. One thing is you can see there's a bit of a hierarchy. It's the hierarchy is a bit inverted. It starts with what you would call the top-level domain. There's very few of those, like edu. What are the other ones? Com, org, gov, mil, right? .mil, military. And then you can see inside of each of those top-level ones, you have second-level domains. For example, within edu, they're all the colleges. Within com, all the companies, and you can go further and further. So it's a bit of a hierarchy. You can think of it as a tree, starting at an unnamed root, then into the few top-level domains, edu, whatever, com, org, net, and then further and further subdomains. Now, so what this means is that the big implication of having names is that when you're going to refer in a program, or when you're talking to somebody with a name to a host that you're talking about, somewhere there has to be a way for, if the routing system is all based on the 32-bit addresses, there needs to be a way to convert those host names into IP addresses. So very early on, they did this by having a file. There's a file called host.txt. That's maybe a good name for it. And that file was just shared with everybody and edited by somebody, and that had the mapping of all host names to IP addresses. This works fine for hundreds or thousands maybe. But at some point people realize maybe we need a system to manage this mapping. It's essentially a distributed database, and that database is called DNS, which you may have heard of as well. So before we talk a little bit about DNS, I wanted to show a little bit of code where we can show how you find the host name yourself. Let me just go ahead and look at that code here. This is not too exciting. This is a simple program that gets your host name. It calls a system call called uname and then prints out the relevant thing. So let me just run it and make sure it works. Yeah. And of course, if you're, we showed that there was a program that I said already existed that did this. And if you want to say, how does it figure out the host name, you can always use strace, our old friend, which you may remember, which shows what system calls a program is using in order to do whatever it's doing. And when you strace host name, if you look carefully down here, you can see, it's a little bit hard to read. You see it's doing a bunch of stuff, but eventually you can see it does this uname, and that uname system call can be used to, sorry, I have to do this version of the system call. Tells you stuff about the machine. For example, that it's running Linux, that it's the name of the host, some other things about the Linux version, what machine, things like that. So ftrace is a useful tool. So anyway, that led us into this. So what do we have to remember? Things to remember. Every machine that you can logically think of as having an IP address, just some 32-bit number, that when we submit a packet, and that packet routing is done at what's called the IP layer. We're not going to talk a lot about how all that stuff happens and how that works. That's the topic for 640 when you take the networking course. But the important thing is, to route packets in IP, you need to have an IP address, which is this 32-bit thing. But we refer to things, or programs generally refer to entities that they wish to communicate with by their host name. The host name needs to be translated to an IP address, and that's done by this service called DNS, just a distributed database. And you can actually play around with DNS if you're interested. There's another program called Dig that you can use. So let's do, if you type like dig and then some host name, which is what I just did, you get a bunch of information back about, which is basically querying the DNS service about this mapping. So you can see things like it says, oh, okay, you know, here I got this IP address back for this host name, and it tells you a bunch of other things about how DNS is doing this lookup, which servers are being contacted in order to get this information. And there's a lot of detail about how DNS works that we're not going to talk about, simply because you could get off and spend days and weeks, and like I said, a whole course on this sort of thing. So if you're interested in that, you can do a man on Dig, which is a DNS lookup utility. And it just exists and is out there, and it's obviously useful. And of course, you can write your own program that does pieces of this too. So here's a program that calls a system call called getHostByName. You give it a host name. It gives you back this structure. This structure has a bunch of things in it, like the name of the host and other names that it may go by, and then things like the list of different addresses that name might map to. It can map to more than one. This program just prints those out. So I'll make all this code available too if people want to look through it, and some of it, of course, will be useful for the pending last project. Okay, any questions about that? Kind of makes sense. We're just doing this at a fairly high level, so we're not going to, like I said, understand how DNS works. So there's a lot of interesting detail there as well. Okay, so we have host names, we have IP addresses, we have some way of mapping the two, but now we need to be able to communicate between, we want to set up a communication channel between a client and a server, for example, or just two communicating processes. They don't have to be structured as a client and a server, though that's a common way to interact. And so we have to have a little bit of terminology. The first piece of terminology is something that people will just call a connection. So to talk to, from one process to talk to another, they have to make some kind of connection. And what people mean by that is a point-to-point communication stream, so two endpoints. Most connections are what are called full duplex connections. What do I mean by that? Pardon me?
Both ways.
Yeah, both ways, right? It does relate to both ways. It means that you can communicate both ways, right? So a single, you might have there are some communication channels which are one way, right? Like Twitter, for example, right? You tweet something, it's kind of a one-way broadcast to many. Of course, people can respond to you in other ways, but you can imagine that as a one-way communication medium, or me yelling at you and not listening to your reply. That's a one-way communication medium. But most communication media are two-way, full duplex. And of course, the ones we talk about today will be that way too. Yeah?
Does full duplex imply that it's the same speed up and down?
No, not necessarily. Yeah. I think people, if they're talking about the bandwidth, they'll talk about upstream bandwidth and downstream bandwidth, and you may say something about them like you have the same upstream and downstream bandwidth. Yeah, symmetric bandwidth, or you might say it's asymmetric, which is very common, like when you're using like your cable modem or something like that. You won't be able to upload as fast as you can download, and there are a lot of technical reasons for that. Okay, so, and then the two types of internet connections that we'll be talking about today, we'll be talking about what are called TCP streams, or TCP IP or UDP IP. The reason they're called that is, well, at the base of both of them is IP, which is a protocol which allows us to, with IP addresses, to route packets from one machine to another. That's just a very bare bones service. On top of that, people have built higher level protocols like TCP and UDP. TCP is the more sophisticated one. It provides what we call a reliable byte stream. So there's two important pieces of that, we call reliable, byte stream. And UDP in contrast is not reliable and a packet oriented. The reliable piece means that TCP, like we talked about a little bit last time, is going to do acknowledgments and timeout and retry and a bunch of sophisticated things to make sure that except in case of disaster, like a machine crashing or some really massive network failure, when you set up a TCP connection between two hosts, it means that when you send a packet, it's going to get to the other side. Again, except in the case of something really horribly going wrong. You can't guarantee that in general because you can't guarantee things like there won't be a volcano eruption or a power loss of the grid and things like that. But within reasonable working confines, a TCP connection once established will by and large mean that a sent packet will get there. And using all the same techniques we talked about last time. For example, you send a packet and then TCP will wait for a while, and if it doesn't get an acknowledgement from the other side, it'll resend it. And it does a bunch of other sophisticated things too to deal with congestion on the internet. And like I said, that's something you can read about on your own time or take 640. So that's the reliable piece. It's a byte stream because it doesn't, even though in the underlying media you're sending packets one at a time, TCP turns that into what just looks like a flow of bytes from the sender to receiver. So I write messages. I may write things that look like discrete messages, but the receiver is just going to receive them as a byte stream. And they may receive them in the messages that we expected, or they may receive them in smaller chunks, or they may receive a bunch of messages at once. It all becomes one blurred byte stream. And so if you're using TCP, you have to figure out how to chop up the byte stream into units that you understand. Let's say I'm going to always send a struct size thing, then I know to read a struct size thing and interpret it or whatever. So does that byte stream concept make sense? Am I clear when I'm saying that? It'll become clear when you're stuck using it, but it basically just means you keep writing, to send messages, you just basically, looks like you're kind of writing to a file, and you keep writing to a file, and the receiver just gets those bytes in order, but they may get them in small chunks or big chunks, who knows what size chunks, so you have to deal with that at an application level. Questions about that? Okay, UDP is a little bit different. It's actually a very thin layer, very simple layer on top of IP, on top of that basic routing service. It's not reliable, much like the underlying IP layer. We talked about some reasons for non-reliability last time. What were those reasons? Do we remember any of them?
Buffer.
Yeah, right. There's limited buffering in the network. So if a lot of packets arrive at a switch or a router or at an end host all at the same time, it might not be room for them, so the router might drop one. And dropping one means it's lost. And everything looks like it's functioning normally, right? But you still can have loss like that because networks aren't constructed to be able to tolerate, the mass load all at once in every space in the network, right? Of course, you could build a network like that never dropped a packet because of buffer overflow, but it would be incredibly expensive. So people don't do that. So because we can lose packets for lots of reasons, that happens certainly at the IP level, but UDP doesn't do anything about it. It just says if you lose a packet, you lose a packet. And it doesn't turn anything into a byte stream. It actually is packet oriented. So you send a chunk, and that chunk is going to arrive at the receiver in one piece. And so it's discretized as opposed to the continuous stream of TCP. And sometimes that's easier to deal with, actually. Okay, so that's TCP and UDP, and those are high-level things to remember about each of those protocols, right? TCP, reliable byte stream. UDP, not reliable, packet-oriented. Okay, any questions about that? Make sense? Okay, we haven't yet you looked at some code. So we're about to look at some code, but we have a few more pieces of terminology. The most important one probably is to know is a socket. A socket is an abstraction of how we're going to deal with, how we're going to interact with it's an abstraction of an endpoint of a communication, of a connection. So a client is going to have a socket, a server is going to have a socket, and we're somehow going to connect those two together to be able to communicate. So it's just an abstraction. It has an address, which is, the machine that you're running on, or actually really the network interface that you're talking over. So that's an IP address. But it also has this one other thing called a port number. So we have this 32-bit IP address, usually IPv4, plus a 16-bit port number. So remember, the IP address identifies the machine when we're communicating. Why do we need a port number? Why do we need more identification of a message? We want to send it to that machine. Why would we need a port number as well as instead of just the machine? Yeah, machines can run more than one thing, right? They can do more than one thing. Right now, for example, you could, I don't know, what can you do, like a netstat? You can see how many, if you do netstat, it's a program you can run on any Unix-based machine. You can see what connections you have open at a given time. You can see there's lots of connections open at once. TCP connections, sometimes UDP, and of course we're not going to sit here and stare at this output, but run netstat for fun. Okay, I'll make that more accurate. Yeah, there's like, people misuse quotations all the time, by the way. There's some sandwich place down there. I just was walking by it the other day and it says like toasted sandwiches. Why do you put that in quotations? Why toasted? Yeah, so it's just bizarre. Yeah, I guess. Yeah, I mean, it made it sound much less appealing, I think. Anyway, we have port numbers because we might have many different programs that wish to communicate at a given point. So just like a machine, you can think of as, and this is, you don't need analogies for this, but you have lots of. If you have, an apartment complex, the port number is more like the number of the apartment as opposed to the street address. So that's a relatively poor analogy, but you get the basic idea. It gives a more specific, hey, I want to talk to this particular thing running on this machine. So machine address isn't good enough to really identify exactly what you want to talk to. So that's a socket always going to be associated then with an address and a port number. And there are really two types of port numbers that you'll run into. We'll show both types today. Let's start with the well-known ones. Well-known port numbers are, for example, if you want to contact a particular service on a machine, like an HTTP server, a web server, there's a well-known port number that's associated with port. Does anybody know? Port 8, just 80, port 80 is a well-known web server. And all services running on a machine, like if you're SSHing into a machine, or you're using Telnet, or you're doing some sort of SCP, or any service where you contact a machine for that service, almost all services each one has a well-known port number associated with it. So when you're going to when someone says contact the web server www.cs.wisc.edu, that goes to a machine that's associated with that name, an IP address that's associated with that name, but it also goes to port 80 because it's a web service. And that makes sense. You have to know where you're want to talk with, whom you're talking with when you want to talk with somebody. For clients, for servers that makes sense. For clients, it doesn't matter so much. So when you create a socket and you're a client, you're going to be talking to, say, a well-known service. You don't have to have a particular well-known number, and so that kind of port number is called an ephemeral port number. It's more assigned when you create the thing, as opposed to using some well-known number. So you just say, give me any port number. And of course, the server essentially needs to kind of know it to talk back to you, but it doesn't really matter that much in general. So two types of port numbers. So if we get to that point, then what we have is a socket is going to be our abstraction of our communication. You can think of a socket as an endpoint. It has an address and a port number associated with it, and therefore a connection is really just defined by a socket pair. It's just, let's say, a client and a server, or just two entities that wish to communicate. Two IP port number pairs, two socket pairs is what a connection is. That make sense? I don't think it's too hard so far. It's going to get worse when we look at some code. Okay, so what we're going to do really the rest of class is just stare at some code. We're going to stare first at, I think, the more complicated code to understand, which is the TCP code. TCP IP, or people will just abbreviate that and say TCP all the time, and they're talking about the same thing. They're not like removing IP from it. There's an interesting history behind all of this socket stuff and how it got invented. There's a group at UC Berkeley that was doing their own Unix version, and that Unix version called Berkeley Unix became very popular. One of the main reasons it became popular is because because they invented the socket abstraction, and it was the first really easy way to program the internet or make programs that communicate. And that using this generic socket interface. And the socket interface is generic enough that it could work on top of any communication protocol, but basically people just use it for either TCP or UDP-based communications. The group that did it, the Berkeley Unix group, did a whole bunch of other interesting things, which we're not going to talk about in here. There was a new file system they built, which was the first kind of disk-aware file system called the Berkeley Fast File System. The same group invented the editor VI, which is a predecessor to Vim. How many people are using Vim in here? Some number of you. So that goes back to that same group. They invented the C shell, which became eventually TC shell, which some of you may use. Lots of things came out of there, and it became certainly on the machines of the time, which were mini computers, it became the most dominant Unix that was running out there. There was also the Bell Labs Unix. But this one had a lot of other benefits, and soon became probably the most popular one. And then got sidetracked for a while in legal battles and companies. And in getting sidetracked, actually allowed for the rise of this other thing called Linux, which arose but didn't have all the legal battles and companies, with their own versions of things. And that's why all those old Unix systems basically went away. Because of that kind of legal stuff going on, and then gave room for Linux to arise. So anyway, that's a little background there. Let's start looking at some code, and we'll look at a little bit of this code, and then we'll take a break, and then we'll look at a little more code. And like I said, we'll look at TCP first, and then we'll look at the UDP. UDP, like I said, is simpler, so we'll just do that at the end. So when you're trying to understand socket code, you have to understand a couple different things. You have to understand what the client-side code is going to look like and what the server-side is going to look like. And they, of course, are different because the server is going to be the entity that's sitting there waiting for messages or connections to be established, whereas the client is going to actively go out and establish that connection. In general, the client side, I guess I wrote this already here, the client side is fairly simple, whereas the server side is going to be more complicated. So let's look at the whole, let me just move this down a second here. This is really the whole client-side things you have to do in order to communicate. The step one here is you create one of these sockets, and you do that with the appropriately named socket system call. So you call into the operating system with something called socket that's going to create a socket descriptor, and we'll look at some code that does that. It's not too complicated. Slightly more complicated piece is then we have to do, and really this is the only other piece that is complicated at all on the client side, which is we need to create the connection. So we need to say, when I have a TCP communication, I'm setting up a full duplex, two-way communication between the client and a server, let's say. I need to say which server I'm setting up that connection with. And so there's a connect system call that's going to do that. So sock is just making the endpoint. Connect is establishing that there's a connection between the two. Of course, we imagine that on the other side there's some stuff going on. We'll talk about that in a second. And to do that, you have to fill in this slightly complicated, but really not that complicated, but it looks complicated when you look at it at first. This struct, the sock address structure, or sock adder in for internet. We'll look at that in a second too. So once you've done this, once you've called socket and called connect appropriately, when connect returns, it means you have this connection with the server. It means the server has done a bunch of stuff too, and there's a whole bunch of messages that get exchanged and handshakes that go on to set up that connection. But that's all beneath your level of concern. All you know is connect returned, and it looks like it's ready for you to use. And the TCP protocol determines exactly what kind of handshakes, and there's a bunch of messages that get exchanged. And like I said, you'll talk about that you'll learn about that if you take 640. What you do after that, and this point is kind of this key differentiator, is life is very easy after step 2. After step 2, you just call read and write. So you've already done this maybe for files. You call read and write on file descriptors to deal with files. With network communication, you call read and write the same system calls. You call them on sockets. So you want to send a message, you say write to this socket descriptor, some number of bytes, of some size. So here, a structure, you give an address, right? It could be a string, it could be an address of a structure, it could be anything. It's just some bytes and some size. And then on the other side, you read them. And of course, if a protocol is well defined, when you're writing, that means hopefully they're waiting on a read, because otherwise it doesn't make a lot of sense, right? So you write, they read, and then they write back, and you read back is a common interaction. That's the interaction we'll develop. So those are the same exact system calls that you. And one of the very interesting things about Unix systems is that any I/O you're doing in general looks very uniform. You can't really tell that you're doing, when you see just the write system call, you can't tell, am I writing to a socket or am I writing to a file? The only way you can tell is by seeing how that descriptor got created. Was it created by a socket call, or was it created by an open call to create, to open a file? So that's a little bit unusual, but that's how Unix works. And then, of course, when you're all done, you call close on that socket, and then you're all done. Though you don't have to do that for a long time. Your TCP connection can be very long-lasting, though a lot of times it isn't. We'll talk about that too. Okay, so any questions about that? That kind of makes sense? So let's look at a little bit of code. Here's the call the socket. That's not that interesting. It takes a few different arguments. Let's look at them. So it takes domain and a type and a protocol, but for anything that we're going to do, which is TCP, this is a TCP one, it's going to say basically the protocol family is the internet protocol family, and that's almost always what you're going to be doing when you call sockets. So argument 1 is almost always going to be this. This means I want to use the internet, and what it really means is you're going to use either UDP or TCP. At that point, you don't know. This next parameter tells the system whether you really want to use UDP or TCP. TCP is that streaming protocol, so TCP means sock stream. As we'll look at some other code later, which will say socket underscore dgram or datagram, which is referring to a discretized packet, which is UDP. But TCP means sock stream, and then most times this last field is just 0 because we don't need any more parameters. So that's not too exciting. It's just how you call to create a socket using internet protocol and sock stream instead of just saying TCP is how you refer to it. Let's look at the next piece, a little bit more complicated. So we've created a socket, but having a socket without connecting to some server to talk to isn't that exciting. So you want to talk to some server. To talk to a server, you need a host name and a port number. And then you need to turn that host name and port number into something that the system understands, which at the lowest level is an internet address or a socket address, which means you need to fill in this structure called a sockadder underscore in or internet. And that has a bunch of different pieces. It has the family that you have to refer to, which is always going to be AF underscore INET for the internet family of protocols. It's going to have a port number, which is this unsigned short, and then it has this internet address, which is the 32-bit. It's a struct, but it's really just the 32-bit internet address as we understand it. So this is a very common sequence. You'll see, okay, first we create the socket. Then given that host name, we call get host by name to get back some more information, like what the actual internet address is of this thing. And then what we do is we simply fill in this socket address, here called server address. We set the family field, see server adder.syn underscore family to AF underscore INET. That's always going to be the case for anything we do in here. They then call B0 to zero out the Oh, this is done slightly incorrectly. It should be like this. This first, it's zeroed out just to make sure there's nothing in the structure. Then you set some of the fields. For example, the family field is set to that. And then you grab, you copy from the get host by name result, this first address, you copy it into the address field of the socket address structure. So again, you look at code like this and it looks horribly ugly, right? But it's really doing a very simple thing. It's just saying, I just want to fill in this structure. And of course, if you want to do this nicely, you'd write a routine that just did this for you. You like that, you know, given this socket address structure and this host name and port number, do this work and then return to me the socket address or connect or whatever to it. And then finally the port numbers filled in here. Now you'll see a bunch of these things, and this thing is, this is pronounced H2N, and the short version of it. Short, like as opposed to an int or something. And what this does is we have this problem that we're communicating between machines is they might not have the same endianness. So remember way back when we talked about endianness, what do I mean by endianness when I was talking about that?
The order that bytes are like represented.
Yeah, perfect. So right, if you have a 4-byte int, you can either go kind of put 0, 1, 2, 3, 4 of that, or low to high or high to low in memory, and different machines do it differently. So anytime you're communicating, there's some sensitivity to, well, we need some sort of agreement. So there needs to be a network agreed upon order so that when you have bytes that you're sending from one side, that they end up on the other side being able to interpret them correctly. And so you'll see a lot of calls like this around ints and shorts and things like that that are packed in these structures, which say convert from the host form to the network form, the network agreed upon byte ordering. And this is a short, that port number is a short, so that's the S piece there. So there's an H to N set of functions. There's also the reverse network to host ordering when you pull things out of these structures. And so you'll see a lot of that. It just makes the code look a little bit more confusing, but it's not anything complicated going on. It's just switching the bytes if you need to. Then the final piece here is calling connect, and you can see connect takes the socket descriptor, which I just called FD here. Sometimes you'll maybe call it SD since it's a socket descriptor, not a file descriptor. It takes the server address and the size of the server address, and you've specified everything that you need to in there already, right? You've specified that this is the Internet Protocol Suite, that this is the specific the IP address that we need, and this is the port number that we wish to connect to, and then connect simply does that work and goes and connects with the remote server. And I guess that's all we'll look at for that piece. So important steps: call socket, then set up the information about which endpoint you wish to communicate on a server, and then call connect. And then you're done on the client side, really. You can just do read and write at that point. Any questions about that? And I guess we could, there's probably an example here that does the next piece. So after connecting here, you can see what this little client does is it simply calls write of a request of some length and then reads a reply. And those are just those system calls that you may have already used, and then does a close. And when you do a write, you're just passing anytime you're using write, you're just passing a pointer and a length. It doesn't care whether those are characters or it's the structure or whatever. It's just bytes that need to be copied from here, in this case, out onto the socket and into some other machine. If it had been a file, it would just copy those bytes to, let's say, a disk or a file on disk. The system calls don't interpret the bytes at all. It's just bytes. And so the fact that I happen to be using a character, passing a pointer to what looks like an array of characters or a string, it doesn't really care about that. It just needs to know where to start and how many bytes to copy. Any questions about that? Make sense?
Why is this equal to RC?
Sorry. Here?
Yeah.
What I'm doing here is what you probably should do here is you should look at how many, if write succeeds, it's going to return how many bytes got written. And so that's what you would just check. What would be logical to check here is that RC is equal to, in this case, the string length of the request. And then down here you could see how many bytes you got in your reply by looking here. Yeah?
You said we're sending our bytes, but the bytes by themselves don't mean anything, right? We need to know how they're encoded. So do we not send somehow? Why do we not send somehow, the encoding system we're using?
So at the lowest level, we just send bytes, and the only thing we're doing here is, if we care about things like how to interpret them, sure, you could do that yourself, but you have to do it. The system isn't going to do anything for you. So if you're saying, I want, for example, when we talk about a web server and how that works, that's a very specific protocol where you say, I'm sending a request and it looks like this, and it's ASCII and you should interpret it this way, and then when I ask for this thing, you should give me this thing back in this very specific format, and there's an agreement, and there's a higher level protocol built on this. This is the lowest level we can get, which is just, it's a reliable byte stream. Everything else that we want to build on top of that, it's up to you to do it. And you're right, you might need to do that. You can't just randomly interpret bytes. You have to know what to expect. But since you're often writing, either you're writing the client and the server, or there's such a well-known protocol that exists on top of this, like HTTP, like we'll talk about next time, that it's not such a big issue. Does that make sense? Other questions? All right, so that's the client. That's a simple piece. The server's going to take a bit, so why don't we take a break right now, and then we'll come back. Let me stop QuickTime for a minute.